Good day, students. Today we will be covering Euclidean spaces. And this is just an outline of today's lecture. We will just have a discussion on how Euclidean spaces are relevant in economic theory, and we'll go on to discuss points or vectors in a Euclidean space. And we will discuss more on three-dimension points as well as surfaces in R3, vectors in a product as well as cross product, and we'll go on to equations of lines, planes. As you all know up to this point that a budget set in a two-good world is given as P1x1 plus P2x2 smaller or equals to I, where I is your income. So in order to think of this line, this is just a line in R2. But in reality, the consumer consumes on n commodity space. So this budget constraint will have to be extended all the way to plus P3x3 dot plus Pnxn is smaller or equals to I. So that's where Euclidean spaces come into place, where we need to familiarize ourselves with points in R, which you are already familiar with. A point in R is just a point on the real number line, and a point in R2, which is a point on a Cartesian plane. But we can deal with points on R3, which will also be a point on your XYZ axis. And to make these ideas more general, we can even talk of a point in Rn or a point in R4, R5, R6. But then as we move on to higher dimension space, it becomes more abstract, as we cannot imagine how these points look like in R4 or R5 because we've never seen a five-dimensional space. In the real world, we're only familiar with three-dimension or 3D. So Euclidean space serves as a reference point where we study objects in higher dimension spaces. For instance, this is the R3 coordinate system. It has the z-axis. So if we are on xy plane, you can think of xy plane as the floor. So a point in xy plane is just a point on your floor where the z-axis is just 0. And the point on an xz plane is just a point on your left wall where the y-axis is 0. And the point on the YZ plane will just be a point on your right wall where your x-axis corresponds to 0. So as I've already pointed out, a point in numbers in R2 are just your Cartesian plane. You've come across Cartesian plane in high school. So the point, or actually a pair AB is associated with a point in R2. You need to know that we call these ordered pairs in a sense that AB is not the same as BA. And a point in R3 is just a triple ABC. And this triple is also ordered as well, in a sense that ABC is not the same as CBA or BAC. The real line is just a single number on your real number line. Your real number line is a straight line that starts from 0 to infinity and from 0 to negative infinity. So your real line is between infinity and negative infinity. That's the numbers on the real number line. The plane R2 consists of ordered pairs, as I've already pointed out. But then if we move on to higher dimensional spaces, these points can go all the way to n, and we call them n tuples, because we start with pairs. We start with a singleton, which is just a point in R, a double, which is a point in R2, a triple, which is a point in R3, and then obviously as we move on to n, these numbers will be n tuples, right? So if we have a vector or a 1 by n or an n by 1 vector, that's an n tuple, because it's a list of number from 1 all the way to n. So such a space is referred as a Euclidean space, and it's written as R to the n. So whenever you see R to the n, it means that we are in n-dimensional space. Where R2 we are in 2-dimensional, R3 we in R3 3-dimensional space, and so on. So in order to think of these points, right, you can just use the right-hand rule, where the thumb corresponds to the z-axis, your index finger corresponds to your x-axis, and the 3 other fingers will correspond to your y-axis. So that's how you can draw your R3 coordinate space. So this point P, ABC, is how you draw a point in R3. For instance, if A corresponds to your x-axis and B corresponds to this b-axis, right? Your B corresponds and C corresponds to the z-axis. So this point here will just be ABC. So it's a floating point on R3. So if you think of it in terms of in the real world situation, so this point is just a particle that's floating in space. So normally we have region representations on R3. For instance, you can imagine how the surface looks like in R3. Z is equals to 3 will just be a plane that cuts through the z-axis at z is equals to 3, and y is equals to 5. As you can see, when y is just 5, it means your x-axis as well as your z-axis are equals to 0. So y will just be a plane that cuts through y is equals to 5, whereas y is equals to 5 in R2 is just a line that cuts through the y-axis at y is equals to 5. So with regards to this equation here, it's defined on your xy plane or on a Cartesian plane, as you would have come across it in curve sketching course, right? Show that ABC represents the rectangular box in R3. I have all of this in the next few slides and it will be clear. As I've already discussed in the previous slide, you can see how our planes look like. For instance, z is equals to 3 is this plane here. It cuts through the z-axis at z is equals to 3, and as you can see, this plane is parallel to the xy axis in a sense that it will never cut through the xy axis, and y is equals to 5 is just a plane that cuts through the y-axis at x is equals to 5, and as you can see, this plane is parallel to the z x-axis in a sense that it will never touch the z-axis. We did say that y is equals to 5. Y is equals to 5 is simply a line that cuts through the y-axis at y is equals to 5. And we don't draw the line y is equals to 5 here because this is a three-dimensional space. Y is equals to 5 in R2 is defined on the xy coordinate space. So we're not going to draw this line here. So with regards to establishing that the point ABC represents the rectangular box, we're going to plot our points. For instance, when A, our x coordinate is non-zero and all other coordinates are 0, it means that we're sitting exactly on the x-axis. And if B, or the y coordinate, is the only non-zero coordinate, it means that we're sitting on the y-axis at B. So it corresponds to the point here. When we're on B, it means all other points, all other coordinates are 0 other than y coordinate itself. So if A, B are non-zero and the z entry or z coordinate is 0, it means that we're sitting on the floor. So we are on the xy plane, as I've discussed previously, that if you're on your xy plane or on the floor, it means the z coordinate is 0. And if you are, when you have a point or a frame on the left wall, it means that your y coordinate will be 0. So we have A0C. So this is a point on the left wall. And then if all the entries are 0 other than Z itself, 0C, it means that the point C is just a point on the Z axis. So we have it here. And then if X coordinate is 0 and you have B and C, which means your Y and Z coordinates are non-zero elements, it means that our point is sitting on the right wall. And then when all of the points are non-zero, it means that our point is floating here. So in this point, as you can see, this C here is parallel. It's the Z coordinate, which happens to be non-zero. So this point, as you can see, it's parallel to the C of the Z axis, right? And then from AB, as you can see, when we on AB, it means that the Z coordinate, if we want this floor, the Z coordinate is 0. So ABC cannot be here. So we move up all the way to the point that's parallel to C. So this point here is ABC. It's like a floating point in space in 3 dimensions. So ABC corresponds to this point. Because it's all our coordinates here are non-zero. So if all our coordinates are 0, it means we're just floating in space. So if we join all our dots, right? If we join these dots, it is clear that this is a rectangular box in R3. And then we have other surfaces, because other than planes, we can have spheres, cylinders, as well as other shapes in R3. We don't necessarily have need to have planes. For instance, we are given this surface here. It's defined as x squared plus y squared is equals to 1 and z is equals to 3. So we can actually define how this looks like in R3. For instance, x squared plus y squared is equals to 1 just corresponds to a circle in R2. That is a circle that's centered at 0 with radius 1. And when z is equals to 3, it means that we need to move our circle upwards until when z is equals to 3. So that's how this surface looks like in R3. And then when we have x squared plus y squared is equals to 1, this corresponds to a circle in R3, right? But if we're in R3, we have no restrictions on z-axis, so this will be a cylinder in R3. You need to do the exercises from the textbook Simon and Blue, exercise 10.1 to 10.4. That's what we're covering, corresponds to chapter 10 of Bloom. I have this in red just to show that it's very important for you to do the exercises, because the standard of difficulty of tests is aligned to that of exercises. So if you want to do well in this course, you should do all the exercises that I recommend you do. For instance, this is what I just discussed. The circle x squared plus y squared is equals to 1, right? But now this circle needs to move further up until it cuts through z is equals to 3. And then in this case, we had no restrictions on our z-axis. So we have a cylinder that goes all the way up to the z-axis. So we can talk about distance in R2, R3, and all the way to Rn. So if you want to move between 2 points in R2, say between AB and CD, you need to subtract the higher coordinates from the lower coordinates. So what you need to do in this case is that you must move between C minus A, right, the higher coordinate minus the lower one, and G minus B, the higher coordinate minus the lower one. And this will be your displacement. A displacement, as you all know, that it has a direction and magnitude. So your displacement is a vector. As you can see, it's in R2. The method of subtracting higher coordinates is also used in R3. For instance, if you need to move between 2 points in R3, your displacement will be PQ, which means you need to move from you need to move B1 minus A1 from B2 minus A2 and B3 minus A3. Even in this sense, we have the higher coordinate, we subtract the lower coordinates. Likewise, if you want to move between two distance in R2, the distance in R2 is actually given as follows. This is just the absolute value of D to show that our distance is always positive. So this distance is a Euclidean distance, and you're familiar with this distance here. So this is just the distance between AB and CD. And a distance in R3 is defined the same way. You need to add the square of your third coordinate. So PQ, we have this just to show that it's a distance. And you need to know that a distance is a scalar. When we work out this expression here, we're just going to end up with a number in R, which is a scalar. We're not going to end up with a pair as in here, because this one is a displacement. We end up with a pair. It's a vector in R2. This is a displacement. We end up with a vector in R3. But with regards to distance, because distance is a scalar, we just end up with a number. So what we're doing here is to find the equation of a sphere. So in R3, any point between the center, any point that lies on the sphere and the center will always be smaller or equals to R. So if P is on a sphere, P is on the sphere if and only if PC is equals to R. When we square both sides, we end up with PC all square is equals to R squared. So the equation of a sphere is given as R squared is equals to X minus A all the way square, all the way to the 2, plus Y minus B squared plus Z minus C squared. So this is how an equation of a sphere looks like. And then we have an example here. So we are given this equation. We are told that it's an equation of a sphere. Now we need to find its center and radius. In doing this, we need to complete the square. For instance, if I have ax squared plus bx plus c, when we complete the square on this equation, what we're going to do is we're going to divide bx by 2. And after dividing bx by 2, right, we get ax plus, we have ax plus b over 2 all the way square. So if we were to simplify this expression further, we get to our original equation. So that's how we complete the square. So this hint will really help us in finding the equation of a sphere. So what we're doing here is that in this step we have x squared plus 4x, right? But x squared plus 4x, if we divide 4x by 2, we have x squared plus 4x plus 4. Can you just add 4 here? I should have added 4. But then because we're adding 4, we on the left hand side, we also need to add it on the right hand side, right? And then with regards to our y variables, we have y squared minus 6y. We divide negative 6 by 2 because our b here is negative 6. For instance, y squared corresponds to ax squared, and negative 6y corresponds to plus bx. So we divide by 2, we divide by negative 3, right? Because we're going to add 3 square, as in here, minus 3 all squared means that we add 9 here. What we do on the left hand side, we do on the right hand side, we get 9 on the right hand side. And then we have another variable z squared plus 2z. 2z divided by 2 is 1. So we add 1 on the left hand side and we should add 1 on the right hand side. So what we end up with, if we simplify this expression further, for instance, if we write x squared plus 4x plus 4, the other way of writing it is x plus 2 all the way square, y squared minus 6y plus 9 is the same as y minus 3 all square. Z squared plus 2z plus 1 is the same as z plus 1 all the way square. If we simplify further, we get 8. Don't forget we should have had 4 here. So when we simplify our expression further, we get 8. So the center of our circle will be -2. Remember the formula of your sphere is x minus a all the way to 2. So it will just be x minus 2. The first component will be -2, and the second one will be 3, and the third one will be -1. So in a nutshell, your center is -2, 3, and -1. And the radius is square root of 8, right? If we simplify it further, it's the square root of, it's 2 times the square root of 2. So that's our radius. So given the equation of a sphere, we were able to find its center and radius by completing the square. If this example is not clear, I have another example. I have 2 more examples in the next slide. So in this class exercise, we need to find an equation of the sphere that passes through the point P and has the center 3, 8, and 1. And we also need to show that the equation given here represents a sphere. In order to show that the equation represents the sphere, it means that we need to find its center and radius, because the sphere is defined by its center as well as its radius. So we have workings here. Because we said our sphere looks something like this for number 1, where, because this is not drawn, we didn't draw it according to scale, our center is at C. We're in R3. So it will be the point here. The point 381 is a floating point here in R3. And obviously when we have negative coordinates, so this will just be a point under the floor. If we dig our floor, we get this dotted line here. So 4, 3, -1 is a point here. It's a point that our sphere cuts through. So we already pointed out that any point, the distance between any point on the sphere and its center is just the radius. So that's what we found, that's what we need to find. For instance, PC square, right? It's 4 minus 3 all the way to square plus 3 minus 8 plus -1 minus 1 square, right? So PC square is just 30. So if we find its square root, the square root of 3 of PC, it means that PC is the square root of 30, which means that will be the radius. The distance between the center and the point on a sphere is simply a radius. You can think of this as the center, though it does not look like a center because this was not drawn according to scale. Which means the equation of the sphere will just be x minus 3. Remember, if this were, we had -3, it was going to be x plus 3. Now it's x minus 3 square plus y minus 8 square plus z minus y square is equals to 30. Remember, it's everything is equals to PC square. not square root of 30, because it's PC square, so it will just be simply 30. But then we were asked to find the radius. The radius is PC, which means it's PC, which is equals to R, is equals to the square root of 30. And then with regards to number 2, we need to complete the square again in order to find the equation of our sphere. Right. So what's gonna happen here is that we were given the original equation. I should have written it here, but let me just go back. X squared plus y squared plus z squared minus 2x minus 4y. So what we're going to do is, in this case, our bx, negative bx, remember when we complete the square, it should be x plus bx over 2. So here we will have x minus 2 all the way square, right? But then in order to make sure that if we say minus 2 square, it means we're adding 4 on the left hand side. Negative 2 square is just 4. So if we add 4 on the left hand side, it means we must add it on the right hand side. You'll see on the working that's what I've exactly done. And if we have y square minus 4y, it means that, no, with regards to x squared minus 2x divided by 2, it's just negative 1 all the way square. It means I will add 1 on the left hand side and I have to add 1 on the right hand side. What you do on the left, you do on your right. And I have y squared minus 4y, which means I will have plus y minus 2 all square, which means I'm adding 4 on the left hand side, and I now have to add it again on the right hand side. And with regards to z square plus 8z, it will just be plus z plus 4 all the way square, which means I'm adding 16 on the left hand side, then I have to add it on the right hand side. So you will just see how I have it written on my solution. Let me just quickly go to that slide. This is exactly what I've done. I like this thing. What we do is x minus 1, right, all square, it's the same as adding 1 on the left hand side, so I have it as plus 1. Y minus 2 is the same as adding 4, because when I simplify further I will have plus 4 term, so I add 4 on the right hand side. And I also have z plus 4, which is the same as adding 16 on the left hand side. I have to add 16 on the right hand side. As you recall, this 15 was part of the original equation. I took it to the right hand side, which means in the previous equation it was negative 15, so I took it to the right hand side. It's now 15. So obviously I will add all of these because they are like terms to get 36. Which means that the equation of the sphere, remember the sign has to change of my centers. The sign of my center has to change. Now the center will be, that corresponds to the x-axis, will be 1. And the center that corresponds to the y-axis will be 2. and the center that corresponds to the z-axis will be -4. As you remember, the equation of a sphere is z minus b all the way square. So it means if I have +4, 4 will be -4. And r square, remember in the equation we have r square, not just r. So which means r square is 36, which implies that the radius is 6. So by completing the square, we were able to find the center of the sphere as well as its radius. At this stage, I take it that you're familiar with adding two vectors algebraically. But vectors can also be added geometrically by the parallelogram and triangle law. For instance, if we have vector uv, so in order to draw these vectors, we use the head to tail method. For instance, our vector v starts at the head of the vector u, which means that we join the tail of v with the head of u, right? And in order to get u plus v, we start at the initial point of u all the way to the terminal point of v. So that's the triangle law of adding two vectors. But we also have the parallelogram law. For instance, if we begin with a triangle, as in figure 3, we have u is this vector and v is defined as the vector that joins the head of u with the tail of v. That's our vector v. With regards to the parallelogram, we now draw a vector that's parallel to v. Obviously, this is v because it's just parallel to v. And we draw another vector which is parallel to u. That vector is the same in magnitude and direction as u. So it's just parallel to u. So this vector is u because it's parallel to u. It has the same magnitude and the same direction. So that's why we call it u. In order to add these our u and v, we draw the diagonal. So that will be the diagonal of our parallelogram. That will be the sum of u, v. And this sum, as in the triangle law, it starts from the initial point of u and it goes all the way to the terminal point of v. So that's the vector u plus v. That's how we add our vectors geometrically. So we have the vectors here, vectors a and b. We need to use the parallelogram law and triangle law to add these vectors. Again, here we also going to use the head to tail method, where the tail of b joins the head of a. Because these two vectors are disjoint. In order to add them up, we need to connect them together and draw and complete the triangle with regards to the triangle law and form a parallelogram with regards to the parallelogram law, and then draw a diagonal, which is going to be the sum of the two vectors geometrically. So with regards to using the triangle law, as I'm using it here, we start with the vector A, right? And then B joins the head of A, because our vectors were disjoint, right? And the sum A plus B starts at the initial point of A and ends at the terminal point of B. So this is A plus B when we're using the triangle law. But now when we're using the parallelogram law, we begin with joining our two vectors as we did in the triangle law. We have our vector A, we join B, B should join A at the head. We join the tail of B with the head of A. Then that's B here, right? Once we have done that, we draw a line that's parallel to B, which is this dotted line here. Exactly the same direction as B, and it's in the direction of B and the same magnitude of B. And then we also draw a dotted line, a vector A that's parallel to A. It's the same magnitude of A and the same direction of A. So this is the dotted line here. Now in order finally to add these two vectors, we need to draw a diagonal on the parallelogram. So our diagonal, as in the triangle law, it starts, we want A plus B, it starts at the initial point of A and ends at the terminal point of B. So this is A plus B. Then that's how we add two vectors geometrically using the parallelogram. So we go on to scalar multiplication of vectors, and it is defined as follows. If C is a scalar and V is a vector, then the scalar multiple of V, say CV, is the vector whose length is C times the length of V, and whose direction is in the same as the direction of V, right? And that's only if C is greater than 0. But then if C is smaller than 0, then the vector CV will be in the opposite direction of the vector V. So in this example here, we need to draw the difference of the vectors x and y using the parallelogram law and triangle law. So the parallelogram law is the mirror image of the triangle law. So what we do here, we can, as we are given the triangle law, so in this case, in this triangle here, we have the vectors y and x, and these vectors start from the origin. And x minus y is the vector that completes the triangle. For instance, remember, if we had to add x plus y, if we had to add them, if we didn't have to take the difference, this vector was gonna start from x and end at the terminal point of y, right, which is x plus y. But now because it's x minus y, it should be in the opposite direction, which is x minus y. So we can, in this case, our slide has been cut here. I will show you in the solution what we need to do here. We need to use the head to tail method, where we're going to, because our vectors are disjoint, right? If we join A with B, it means that the tail of B should join the head of A. So it means that this B will move to here to join the vectors. But now, here we need to add these two vectors using the parallelogram and the triangle law. So we need to find A, negative 2B, right? As we have already alluded to the vector multiplication, negative 2B will be in the opposite direction of B, but twice as large as B. So it will be greater than, it will be in length, it will be greater than B, but it will be in the opposite direction because now we referring to negative 2B. And after that, we join these vectors by starting at A and ending at the terminal point of B. And when we do the parallelogram, we're going to draw a vector that's parallel to negative 2B and the one that's parallel to A, and then we add them up by drawing the diagonal. So I have the solution in the next slide. This is how we will add these. For instance, this should be B, not A. Please fix this, because we say that B, negative 2B, is in the opposite direction of B. As you can see, negative 2B is larger than B, is twice as large. By visual inspection, you can see that it's large, right? And our vector A is here, right? So in order to get A minus 2B, right, we draw our vector here, right? If it was A plus 2B, we will start at the initial point of, if we were to find A plus 2B, we will start at the initial point of A and end at B. But now because it's A minus 2B, this will point in the opposite direction. And then when we use the parallelogram law, we draw vectors. We draw a vector which is a dotted line, it's parallel to A, and draw another vector which is parallel to negative 2B, right? And then we have to draw that diagonal to add these vectors up. If it were A plus 2B, we will start at the initial point of A and end at the terminal point of 2B. But now because we want A minus 2B, the direction will change as it changed here. So it's A minus 2B, but it's going this direction, not the other direction. So that's how we will find the difference between two vectors using the triangle and parallelogram law. We have some summary. We have the summary and other properties of vectors and scalars. So the sum of two vectors u and v is the diagonal of the parallelogram law. Subtraction is the vector that will complete your triangle. So scalar multiplication is defined for vectors in Rn, and we use distributive law as mentioned in these two points. For instance, if R and S are your scalars and U is a vector, we can distribute this vector U over R plus S to get RU plus SU, right? And we can also add the two vectors and multiply them with a scalar R. So we have RU plus RV for all scalars r and vectors u and v. Note that this r is not a vector. It's a scalar. If it were a vector, you will use your matrix law. Remember, you covered matrices. You use matrix law to multiply two vectors. But because r is a scalar, we are allowed to do this. This text is in red to show that it's very important. So it is very crucial for you to go to the textbook Mathematics for Economics, for Economists by Simon and Bloom. You use that textbook, you will do exercise 10.5 to 10.8. Now we move on to inner product spaces. Let V be a real vector space. Suppose to each pair of vectors u, v, an element of V, there is assigned a real number denoted by, this means u dot v. It's denoted by u dot v. This function is called a real or inner product on V if it satisfies the following axioms. It satisfies the linear property, which means I can use this V to multiply my first component, which means that if AU1 plus BU2 dot V is just the same as AU1V plus BU2V. You need to know that these are vectors, and this will be a scalar. RU dot V is the same as RV dot U, which for all scalars, and that is symmetry, in a sense that U dot V is the same as V dot U. And we have the positive definite property, in a sense that when you dot a vector with itself, you end up with a positive number. And if you dot U with if you get U dot U is equals to 0, that can only happen if U is equals to 0. And this property is known as positive definite property. Now we need to use the linearity property of inner product to solve this dot product here. We can do that in the next line. For instance, what we have here is we're going to multiply everything the way you multiply out the brackets. So we start with 3 times 2, 3u1 times 2v1. So it will just be 3, it will be 6u1 dot v1, and we'll have minus 15 u1 dot v2, and we will have 18 u1 v3. And then when you come to the negative 4 u2 is the same as negative 8 u2 v1 plus 20 u2 v2 minus 24 u2 v3. And we cannot simplify this further because we don't have like terms. If we had like terms, for instance, if we had u1 v1, and if this was also u1 v1, we will subtract negative 15 from 6. Now, because none of these are like terms, we cannot simplify any further. So here we continue with the angle between two vectors. The angle between two vectors, in order to define the angle between two vectors, we need to be familiar with the concept of dot product or inner product space, but we have already done that in the previous slide. For instance, for any non-zero vectors u and v, an inner product space V, that is the angle between u and v, is defined to be the angle such that theta is between 0 and pi. Remember, we're dealing with radian measures here. Pi is the same as 180 degrees. But because in this course, we don't use the degrees Celsius, we use radian measure, we say pi. So even in your calculators, when you work out these problems, always convert your calculator to radian measure, not degrees, because we measure our angles in radian measures. And cos theta is equals to u dot v over the distance of u and the distance of v. This should be v, not u. Please just take note of that on your slide. And by Cauchy-Schwarz inequality, cos theta is between -1 and 1, and so the angle exists and is unique, right? And then we have the theorem here. So when we have the angle between u and v in Rn, so you have that u dot v, if u dot v is greater than 0, it means that the angle is acute. And if u dot v is smaller than 0, then the angle is obtuse. And if u dot v is equals to 0, then the angle is 90 degrees. Is pi over 2. The vectors I, j, and k, these are very important vectors, and they called basis vectors. You will cover basis in the chapter of linear independence. Then you'll know what a basis is. But these vectors are quite important because they are basis vectors, and they defined as I is 1, 0, 0. It means that we have 1 in the first component and 0 in the second and third. And j, this one should not be u, it should be j. Please take note of that. J is 0, 1, 0, and k is 0, 0, 1. We need to express A1, A2 in terms of I, j, and k. Right? We have all these examples. We need to do all of them. So I'll move on to the next slide just to show you how I worked all of these out. So in order to express A1, A2 in terms of IJK, it means that I can add them up. So A1I plus A2J plus A3K is just the same as A1, A2, A3, in a sense that I, as you have already pointed out previously, I is 1, 0, 0, right? And j is 0, 1, 0, and k is 0, 0, 1. Because this A1 is a scalar, I can take scalar multiples. This is valid. A1, right? A1 times the first component, this is a scalar, it's just A1. And you multiply everything by 0, you get 0. And then I move on to A2. A2 times 0 is 0. A2 times 1 is A2. A2 times 0 is 0 plus 3. A3 times 0 is 0. A3 times 0 is 0. and A3 times 1 is A3. So I add all of these vectors here. These are vectors in R3. I can add them up because they are of the same dimension. A1 plus 0 is A1. 0 plus A2 is A2. 0 plus A3 is A3. So if I am given any vector, A1, A2, A3, I can express it in terms of my basis vector, right? Basis vectors are very important in a sense that if I take any vector in R3, it can be expressed as a linear combination of the vectors I, j, and k. That's why we call them basis vectors in R3, right? So as you can see that I do end up with A1, A2, A3, which is the same as A1i plus A2j plus A3k. So in number 2, if we can just go back to remember what the question was with regards to number 2. Okay, we were asked to express 1 minus 2, 6 in terms of I, j, and k. As you can see, y minus 2, 6 is just equals to I minus 2j plus 6k. So I can write this vector 1 minus 2, 6 as a linear combination of I, j, and k. That's what it simply means. And then the previous question was, if a and b is equals to this and b, express vectors 2a plus 3b in terms of I, j, and k. Okay, so it's 2a plus 3k, if I remember. 2a plus 3b, and b is given as such. So what I did here, I simply substitute. A was given as this, and b was given as that. So I multiply, because I can multiply a scalar with a vector. So I take the scalar multiple of b, right, to get 2i plus 4j minus 6k. I take a scalar multiple of b, which is 3. I get 12i minus 21k. I add all my i's together to get 14i, and the j's together, 4j plus 12. Okay, 4j does not have a like term, it's 4j. And then negative 6k minus 21k is negative 27k. So that's how I expressed that vector in terms of I, j, and k. And here, if we go back to number 1, to our exercise to remember what the question was, find the unit vector of A. Actually here I just assume that A is the A from number 3, because A should be given as a vector in order for me to find its unit vector. At this point, it's very important to remember that a unit vector is just a vector divided by its distance. So in order for me to find a unit vector, it means that I have to find the distance of the vector A from the origin. Okay, so I assume that A is I plus 2j minus 3k, right, which is just the same as 1, 2 minus 3, right? If I replace my I, j, k, my basis vectors, I get this. Now I need to find the distance of this vector from the origin, right? Remember, the distance from the origin is just 1 minus 0 all square plus 2 minus 0 all square minus 3 minus 0 all square. So it's just the same as taking the square of all these components, of all these vector components, right, and find that square root. So I have 1 square plus 2 square plus minus 3 square which is square root of 14, right? So the distance is the square root of 14. So finally, I need a unit vector. So the unit vector, I just have A hat here just to show that A is different from A. A hat is a unit vector. So I divide every component of my original vector A with its distance. That's a unit vector. 1 over square root of 14 plus 2 over square root of 14 minus 3 over square root of 14. So this vector, if you can check on your own, if you get the distance of this vector from the origin, I reassure you that the distance will be 1. Hence the name unit vector, which means its magnitude from the origin is 1. In the previous slide, the question was we need to find the angle between two vectors, our two vectors A and B, right? So remember, in order to find the angle between two vectors, we just need to have the cos of theta is equals to A dot B divided by the distance of A and the distance of B. So the distance of A, right, which is a norm, and norm is just the distance of a vector from the origin, will just be, remember, A was given as 2, 2, negative 1. So it's just the square root of 4 plus 1, which is 9. The square root of 9 is 3, right? So the distance of B from the origin is 25 plus 9 plus 4, which is the square root of 39. Now it remains to find the dot product of the two vectors, or the inner product. As I did mention in the previous slide that whenever I ask you to find the dot product, the final answer should be a scalar, just a single number, because a dot product is a scalar or just a real number. So here we go on to find our dot product. 2 times 5 is 10, we have 10. 2 times negative 3 is negative 6, we have negative 6. Negative 1 times 2 is negative 2, we have negative 2. We simplify further, we get 2. So the cos of theta, we have A dot B, we have the distance of A and B. It means we're in position to find the angle between these two vectors. A dot B is 2. And the distance of A is 3, that of B square root of 39. I simplify further. I use second function cos of 0.11. I get theta is 1.461. You need to note at this point that my calculator is in radian measure. Just make sure that your calculator is in RAD, not DEG, because in this course we use radian measures, not degrees, to get our angles. And I recall number 6 was, let's just go back. In number 6, we need to show that 2i plus 2j minus k is perpendicular to 5i minus 4j plus 2k. But you need to remember that two vectors are perpendicular when the dot product is equals to 0. So what we need to do in number 6, we just need to find the dot product of these two vectors. If it's 0, then two vectors are indeed perpendicular. This is what we did. We get the dot product. 2 times 5 is 10. 2 times negative 4 is negative 8. Negative 1 times negative 2 is negative 2. 2 minus 10 is 0. Therefore, these vectors are perpendicular. Then we move on to projections of vectors, right? So if we have our triangle here, the projection of A onto B is a vector, right? Because it has a magnitude and a direction. So a projection of B onto the line perpendicular to its scalar is given as B cos theta. The projection of B onto the line perpendicular to it is the scalar B cos theta. So if this is the component of A along B, we have that the cos of theta, right? The cos of theta is its adjacent over its hypotenuse. So we will have cos theta is equals to the component of A along B over the magnitude B, right? Which is what we have here. But in this case we simplified further. So we get that the cos theta is the component of A along B over B, right? Which means over the magnitude of B, which means the component of A along B is B cos theta. If you can just write that and simplify further, you will see that that's the case. But cos theta is the angle between A and B, and it was defined as we previously defined it in our previous slides, right? Hence, the scalar component of B along A is given as comp AB is equals to B cos theta, where cos theta is B dot A over B, the magnitude of B times the magnitude of A. The magnitude of B and that of B will cancel out. So the component of the vector A along B is B dot A over the distance A. The vector projection of B onto A is the scalar component of A along B with the unit vector of A. So what I'm going to do is, remember how we define the unit vector? The unit vector is A multiplied by the magnitude of A, right? A, which is a vector, which is this equation here, right? So by definition, just to summarize the points that we have discussed, scalar projection of B onto A is the component of A onto B, which is equals to B dot A over A. The vector projection of B onto A is projection of A, the projection of A along B, B dot A over A squared times the vector A, right? We don't have B dot A is a scalar, A is a vector, and A, the magnitude of A all square is a scalar. So this is a vector, whereas the component, the scalar projection of B onto A is a scalar. So in this example here, we need to find the vector projection of B onto A, right? So the vector projection of B onto A is given as this according to the formula. I only have the A hat here to show that A is a vector, right? This A is a vector. So I first need to start with the dot product. B dot A is 112 dot negative 231, right? 1 times 2 is -2, -2 plus 3 plus 2, so the dot product is 3. The distance, the distance square, right? Because that's I need to find this expression, is just 1 plus 1 plus 4, which is 6 of a. 1 plus 1 plus 4, it's just 6. I'm not taking the square root because I'm only interested in a square, not the norm a square, not the distance. So I will leave it as is. Now what I have to do is just the substitution. So I get 3 over 6, 1, 1, 2, which is the same as a half. So the vector projection of B onto A is just half, half, and 1. And this is a vector. If I ask you for a component of B onto A, if I ask the component of B onto A, you were supposed to get a scalar. But because I asked for the projection, you end up with a vector in R3. Now we move on to cross products, right? We define cross products. Given two vectors A in R3, A1, 2, and 3, and given that B is B1, B2, B3, it's important to find a non-zero vector C that is perpendicular to both A and B, right? If C is such a vector, then A dot C is equals to 0 and B dot C is equals to 0. And such a vector can only be defined by a cross product. If I can find A cross B, right, my vector A cross B will always be perpendicular to A and B. And we have a formula that we use to find our cross products. So it boils down to this definition here. Given that A is equals to A1, A2, A3, and B is equals to B1, B2, B3, the cross product of A and B is the vector A cross B and is defined as A2, B3 minus A3, B2. That's the first component. The second component is A3, B1 minus A1, B3, and the third one is A1, B2 minus A2, B1. It's important to know that the cross product is a vector, whereas the dot product is a scalar. So I will never give you the formula for the cross product. I expect you to know it. But since you cannot remember this expression, it looks a bit complicated. I wouldn't remember it myself, but there's a technique that you can use to remember this expression here. That is why I will never give you a formula for a cross product, because you need to know that technique, right? So what we use is I get ijk, right? I have ijk here and I have a1, b1. In order to get the first component, I block out this I here, right? So I get the first component, I multiply it the way you would when you get your determinant. I go a2 times b3, it's a2 b3 minus b2 a3, right? Then that's my first component. And then my signs should alternate. So I have minus j. With minus j, I block out the jth column. Then what I do is, I have minus j. It becomes a1 b3 minus b1 a3, right? So this is my second component. To get the third component, I block out K, and then I get A1 B2 minus A2 B1. Remember, the K is positive, so the signs will alternate as when you find the determinant. And this technique will help me to remember my this expression of a cross product instead of memorizing it as is. So we have a few properties of the cross product, right? First of all, our cross product A cross B is orthogonal or perpendicular to both A and B. If theta is the angle between A and B, and theta is defined between 0 and pi, right? Pi is just the radian measure of 180 degree. Then A cross B, A cross product B is equals to AB, the sine of theta. Two non-zero vectors A and B are parallel if and only if the cross product is 0. So if I give you two vectors and I ask you to tell me if they parallel or not, another way of doing that is just to find the cross product. If the cross product is non-zero, it means that they're not parallel. The length of the cross product determined by A cross B is the area of the parallelogram determined by A and B. The volume of the parallelepiped determined by vectors A, B, C is the magnitude V, A dot the cross product of B and C. So what we have here, we need to find a vector that is perpendicular to the plane that passes through points P, Q, and R, and we need to find the area of the triangle of P, Q, and R. Once again, we have the exercises that you need to do, and these exercises are highlighted in red to show that they're very important. So I expect you to attempt all of these exercises on your own. They will not be for hand-in, but for practice purposes. So in order to find a vector that's perpendicular to this plane, if you were to draw all these points, right, you will see that in order for the vector to be perpendicular to P, Q, and R, it should be perpendicular to PQ, right, the displacement PQ and the displacement PR. If such vector is perpendicular to those two displacements, then that vector will automatically be perpendicular to the triangle PQ, which is what we did here. We first start with our displacement PQ. Remember, the displacement PQ is the terminal point, which is Q, minus P, which is minus 1, which is the initial point, right? And PR is the terminal point, which corresponds to our the components of R. That will be 1 minus 1, negative 1 minus 4, 1 minus 6. So we get that PR is 0 minus 5 minus 5. Remember, what we're doing here is that we subtract the terminal point from the initial point. So PQ dot, we want the cross product now. Remember, we use the trick PQ cross PR, the cross product of PR. What we do, in order to get the first component of our vector, we block out the I column. So we get negative 5 minus negative 5 times negative 7 is 35. So we have minus 5 minus 35. J will change in sign. It's not plus J but minus J. We block J to get the second component. That will be 15 minus 0. So we have minus 15J. Plus, we block out the third component, which is 15 minus 0. So we end up with negative 40I minus 15J plus 15K, which corresponds to negative 14 minus 15 and 15. Remember this vector here, we divide by 5. It's a multiple of 5. So it means that negative 8 minus 3 as well as 3 will also be perpendicular to the triangle PQNR, right? So we need to get the area. We were also asked to get the area of the triangle PQR, right? But remember, we were told that the area of the parallelogram is the same as the dot product, the cross product of the two vectors. So the cross product of our two vectors is given as this, right? The distance of the cross product corresponds to the area of the parallelogram, right? So in order to get the area of the triangle, we divide the distance of the parallelogram by 2, which is what we did here. So the area of the parallelogram is the distance of the cross product. We get it, the Euclidean distance, then we divide by half in order to get the area of the parallelogram. We will end here on cross product, and in the next lecture we will cover planes. Thank you for listening. See you in video 4. This will form video 3. The next video will be video 4.